Hello everyone, and welcome to our presentation on implementing scan DFT on AFTx07. I'm Seongwon and I'm joined by my co-presenter
Raghav, Srivaths.
Our contributing authors are Benjamin Ryu and Henan Wang, and we'd like to acknowledge our mentors, Dr. Mark Johnson and Abinand Ramshankar. Today, we'll walk you through the basics of our approach, our implementation steps, and the results we've achieved. This semester, our goal was to implement DFT on the AFTx07 chip using Synopsys Fusion compiler, inserting scan chains, running ATPG, and exploring design, compression, and power-saving techniques. So why test? Before we dive into the implementation, it's important to understand why testing is such a critical step in the design flow. As the slide says, without testing, nothing shifts. You can design the perfect chip, but if you can't verify that it works under all conditions, it's practically unusable. As we move to smaller technology nodes, the risk of failure increases. Testing helps us catch those issues early, especially after RTL verification and before synthesis. While traditional checks like LEC, LDRC, and STA validate logic and timing, DFT specifically helps us evaluate how testable the design is. An alternative DFT method is LBIST, or logic built-in self-test. But in our project, we focused on scan-based DFT. Since I went through all the concepts in detail last semester, I will go through the concepts very quickly this time. In scan DFT, we replace regular flip-flops with scan flip-flops that have a multiplexer to load test data. These are connected in a scan chain, which let us shift test patterns into the circuit and observe outputs at the end. We also use scan compression to reduce the number of test patterns and minimize test time. This setup improves observability and controllability, which is the two key metrics in testability, by allowing ATPG tools to generate efficient patterns for fault detection. This slide shows the actual scan insertion process using Synopsys Fusion compiler. We first define DFT-related signals like the scan clock and reset. Then, we create scan ports for scan data inputs, outputs, and the scan enable signal. Each of these ports is mapped using set DFT signal specifying their type, such as scan data in, scan data out, or scan enable. We also set the scan chain configuration here, using 4 chains in our case. Finally, we run a sequence of comments to create the test protocol, run DFT role checks, and preview the scan structure and insert the scan logic. This grid forms the foundation of how scan is actually implemented in the design.
So we focused our scope for synthesis at the submodule level instead of starting directly at the top. We initially faced a lot of errors like having no command for netlist generation, incorrect design name, wrong comments, and other syntax errors. But once we parsed through and debugged the basic synthesis errors, we inserted scan chains, as described in the previous slide, for both the UART and PWM submodules. We successfully ended our synthesis with no DRC violations and successful DFT scan insertion. After the scan insertion and synthesis, we move to ATPG, or Automatic Test Pattern Generation. This is a tool that automatically creates optimized test vectors to detect faults in digital circuits, giving us high fault coverage and reliability. The goal is to simulate how the circuit would behave in both normal and faulty conditions, then generate input patterns that expose those faults at the output. On the right, it shows how ATPG identifies a fault list, generates a test pattern for each fault, and then optimizes the final pattern set. This process helps us reduce both test time and cost by minimizing the number of patterns while still covering as many faults as possible. As you can see on this slide, we have the results from our ATPG test coverage analysis from the Synopsys SolveNet lab assignments. After running pattern generation on the inserted scan chains, we achieved a high fault coverage ranging from 95 to 99% for stuck-at faults, depending on the block. This level of coverage indicates that the majority of potential manufacturing defects can be detected using our scan patterns. Any remaining uncovered faults are usually due to design constraints like untestable logic or redundant paths. Overall, the result validates the effectiveness of our scan insertion and ATPG setup. Moving forward, our plan is to fully synthesize the top level design and with scan insertion and ATPG implemented on a real tape-outable module. We also plan to, with the help of on-chip clock controllers, handle slower scan shift in speeds and save test time by using fast launch and slow capture. We also have plans to explore ATPG compression because right now only 2% of the ATPG bits are care bits, so there's room for optimization. We'd like to thank Adam Cron from Synopsys and Akshat Ravikiran from SoCET for their help and guidance. Thank you.
Thank you.